Thank you everybody for joining us today. So today's session is our 101 and it's being run by Keith Sisson on terms and concepts for zOS. So I'm sure you will all find this very useful. The session code for today is 6AT. So I will paste the link for the feedback in the chat a bit later on as well. So please do give feedback. All the great things that you experienced today and listen to from Keith, and any feedback on how we can maybe improve things in future sessions as well. And also we do have something to mention around some charities as well. So Keith, if you go to the next slide, please.
Okay.
So this year we are raising money for two really good causes: the RNLI, the Royal National Lifeboat Institution, and Guide Dogs for the Blind. So once again, I will put the link for charity donations in the chat. So if you do feel that you'd like to make a donation, then please do so at that time. The session is being recorded, so you can catch up again later on if you need to. And also I wanted to say that Keith is quite happy for you to ask questions as we go through the presentation, so no need to wait until the end. So I will give you all the privilege to unmute as and when required, but please do stay on mute unless you have a question or comment to make. So with that, Keith, I'll pass over to you, and please do carry on.
Great, thank you, Atul. Good morning, good afternoon, everyone. Really excited to be here. I'm coming to you live from Houston, Texas. It's currently 4:30 a.m. in Texas, but it's going to be a bright day here, so hopefully you'll all have good weather and experience wherever you all are. So this presentation I've done a few times at GSE and other places, and it just started out as a virtual data center tour, and then in the times that I was giving the data center tour, I noticed that there was lots of terms that I was using that people were maybe not familiar with. So we thought it was good for the 101 session to go through some of the terms. Most of the terms I'm going to try to give a pretty straightforward explanation. I'm going to try to give a relatable example of what they are. I'm going to really explain at a very high level what they are. At the end of the presentation, I'd like you to be able to at least relate and understand when you hear some of these things. I really want you to get something out of this. So please, as Atul said, please feel free to unmute and ask a question, or put a question in put a question in the chat. So don't hesitate, let's participate, and let's go from there. So all of these terms out there that you see, they sometimes can be daunting, sometimes can be overwhelming, and so I want. I'm sorry, Mackenzie, I didn't quite get all of that.
I think that was just some background noise. So
okay.
Keith, carry on.
All right, okay. All right, so let's start off with the very basics. So we have the zOS Z system hardware. So this is a picture in a data center of three mainframes sitting in a row. So they're approximately 45 centimeters wide and about 2 meters tall, which is the normal size for a piece of equipment in a data center. So in this particular example, those two on the outside are Z15 mainframes, and the one in the middle is a Z14. So on the outside, you really can't tell too much difference between the generations, the last few generations of mainframe. You can see the style of door is a little bit different. So they're known as System Z because the Z stands for zero downtime. Many people call them CECs or CPCs. So instead of the actual name for the mainframe is a CEC, a Central Electronics Complex, or a Central Processor Complex. I prefer the term CEC, but a lot of times you'll hear CPC, but that's what they're referring to, the entire piece of equipment, not just the old-fashioned term, I guess, would be mainframe. So the mainframe itself, you might hear the term MIPS. And what MIPS is it's a measure of the capacity of the machine. They don't go by megahertz or gigahertz or CPU speed or capability. They go by millions of instructions per second. The higher the millions of instructions per second, essentially, the more it will cost you to operate the machine. The technical term for MIPS that's used is MSUs, millions of service units. Again, this is a measure of the theoretical capacity of the machine to operate at speed. So why is that important? That is important because everything associated with the mainframe, all the software that you buy for the mainframe is basically paid for by the capacity of the machine to run it. So the faster and the more instructions that you can execute, the more you pay for the software. So that's a very fundamental part of how the mainframe has operated for a long time. So what they do is, to be fair, there are many vendors, including IBM, that use a 4-hour rolling average to calculate the capacity of the machine that you actually use. So you're not paying for the entire amount of the machine, you're paying for the capacity that you actually use. So what they do is they take a 4-hour period where you use the most average MIPS or MSUs, and then they use that as your benchmark for how much the software charges will be for that month. Now that's a kind of a complicated way of doing it, and there was all sorts of things that went into trying to reduce that monthly 4-hour average. So that's when IBM came out with a new methodology called tailor-fit pricing. And basically that means you are charged for the consumption on the machine as opposed to this average 4-hour rolling average. So in many cases that can, because it's actual consumption, it can be more economical for people using the machine. All right, so I'm going to open the door here. This is in the data center. This is actually in the data center for BMC software. This is the data center that we have in Detroit. So it's kind of a little bit boring on the inside. There's some lights on the fans on the bottom half of the machine. You know, not too exciting when you have people in and you're giving them a tour. It's not overly exciting to show them this. But it is interesting to note that in this particular model, this is a Z15, the entire top half of this machine is empty. So really the entire CAC is this bottom half of the machine. So I do have a picture of a Z13, and I'm going to open the door so you can see a little bit more about what's in this machine. Okay, so in the US, I would say that this is about the size of a large refrigerator. I guess in Europe, it would be an enormous refrigerator. But the top parts of this machine are the support elements, power and other things that go into it. The middle part here is the processor drawers, and I'm going to go into what that means. And then the bottom, there are some channels and some cards that are plugged in that allow you to do some things. I'm going to go into a little bit more detail on that. So processors are made up of, the processors in the drawers are virtually the same hardware, but they can be configured to operate a little differently. The most common one would be a GP, or a general purpose processor. That's where all of the instructions for your machine are actually executed. In addition to that, there is what's called a specialty processor engine. That's a zip engine, Z-I-I-P, and that is used to run Java workload. Now, the interesting thing about a zip engine is that it does not count towards the MSUs towards the machine. So you don't pay for code that is executed in a zip engine. And it's specifically designed to run Java and some other things that don't run in the GP. And that is to encourage people to use Java on the mainframe and also to reduce your overall costs for the mainframe if you are a Java-based environment. So there's also another type of CPU in this processor drawer called an ICF, or an internal coupling facility. And I'm going to explain a little bit why that's useful in a few minutes. Another one would be an IFL. And the IFL is another engine that is designed to run Z Linux work. This IFL engine also does not count towards the capacity of the machine. So it's essentially a free workload in terms of MSUs and the tailor fit pricing and the monthly 4-hour average that we were talking about. The zip and the IFL do not count towards that. All right, so down here in the bottom, in the channel cards, we have primarily what we have is an open system adapter, or an OSA card. That's just a network card for the mainframe. Prior to even TCP/IP being widely available, the mainframes had their own proprietary networking protocol called SNA. Now the modern mainframes are all connected to the TCP/IP network, just like any other devices. So that's an open system adapter. That's what that means. There are other cards in here, crypto coprocessors and some FICON cards. And I'm going to go into a little bit more detail about what a FICON would be in a second. So let me talk a little bit more about the processors. So there's two processors that are the heart of the mainframe. There's a system controller, this SC chip, and a processor unit chip. So all of those general processor, IFL, ICF, all of those types of engines all run on this red side, the processor unit chip. And how that works is those processor units are controlled by a system controller chip in a drawer. So let me just show you kind of a picture of a drawer to kind of give you an idea of where we are in this. So the system controller chip coordinates the activity between the 4 processor unit chips in this example drawer. And it also controls the communication with other processor drawers that you have. So this is why the machine can operate at tremendously fast speeds, because this controller, these drawers and operated by the system controller really help speed the efficiency of the mainframe. Again, as I'm going through this, if there's things that you want to unmute and ask about, please feel free to do that. And Atul, if you see anything that comes up in the chat, just interrupt me and ping, and we'll go through. Okay. All right, so to go on, the newest IBM chip is the Telum chip. And the Telum chip is going to be in the next generation Z processor, which will be coming out sometime soon. So that it is a 7 nanometer chip. So 7 nanometers. 7 nanometers refers to the size of the transistor that's on the chip. Okay, so there's 22.5 billion transistors on the chip for this new system. So 22.5 billion chips, and they're 7 nanometers long, each one of them. To give you an idea of scale, the thickness of a human hair is between 80 and 100,000 nanometers. So a 7 nanometer size is unbelievably small. And I read an article recently that the IBM is working on a 2 nanometer chip. So it's just incredibly small to fit. Obviously, you're fitting billions of them on this chip, so they've got to be incredibly strong. give you some context, they're about the same number on a sophisticated Apple M1 chip is 16 billion processors. The rest of the processors, have billions of them on there. IBM's chips are specifically and specialty designed. They're a little bit larger than a normal chip you would see in a server type of a device. All right, so what are some of the things that are connected to the mainframe? So I'm showing this picture of a very old data center with DASD devices. That's how you would pronounce that, DASD. And that is a direct access storage device. That's a disk. So this is from circa 1975. And each one of these machines is about a 3 gig hard drive. So you can imagine that if you were connecting all of those, you'd have to name each one of those devices so that you would know. So you wouldn't have a C drive and a D drive and an E drive like you might have seen on servers in the past. They are using what's called a VALSEER, and you pronounce it out volume serial, but it's a VALSEER. So each one of these has a 6-character VALSEER associated with it so that it can address all of those devices. And in a full data center, you would have like hundreds of rows of these. So you would have many, many of these devices. So that's what it was in circa 1975. So now, the mainframe technology, looks pretty much like you would expect any other server type storage to look like. It's a Hitachi example, Dell EMC examples. This is an IBM example. But the idea is it's really all either solid state or spinning drives on their side that make up all that capacity. So you no longer have rows and rows of all disk. You have a single bank of disks. Now, what's interesting about that is, as the mainframe and IBM's philosophy around the mainframe has always been to advocate for the customer so that the customer can take advantage of new technology without them forcing them to change their processes, to change their workflows, to recompile or assemble their programs. They just want it to work. They want you to go from generation of equipment to generation of equipment. So what I wanted to say is an example. You saw that rows of equipment with the circa 1975 DASD. Each one of them had a VALSEER. Well, the VALSEERs are still there, but they're just striped across this bank of disk in this new modern array. So you have all of the speed, all of the modern disk, all of the modern amenities that you would expect, and even more robust. But you still have the philosophy of VALSEERs. So that might be confusing to somebody. It's not each one of these devices as a VALSEER. It's spread over this entire thing. It's striped. But the point is that IBM has allowed you to refer to VALSEERs in the same way that you always did, but capitalize on new technology. It's the same thing with virtual tape. This is another type of device that you would connect to the mainframe. You might be like, what the heck, why would we need tape? So originally, back when, you would have used tape to back up things because tape is a cheaper medium and more storable than disk was. So you would write a batch job, which is just an automated workflow, to take data from your disk and put it on tape, and then you would take the tape off-site to be protected. So instead, now we have virtual tape. And virtual tape, again, here's a Dell example. It's just another, looks like another modern DASD array or disk array. IBM has the TS7700. But if you open them up and look at it, again, you see that it's just disk. But you're allowed to write to it as if the operating system thinks you're writing the tape. And the way that works is this is a Luminex example. The Luminex and all of the others emulate a tape drive, and then they use some sort of storage media to emulate the tapes. So you can write to a tape, quote unquote, and it's really just creating a file on disk. And then the disk usually replicates somewhere offsite. So you don't really have any tape handling or tape motion, but this is a really nice way of automating backups for mainframes. These two things on top here, it's kind of interesting to note. Those are Linux ZPD boxes. So a ZPD or an RD&T boxes are mainframes that run under a Linux operating system. So these are both running zOS, and they're very small capacity and they're self-contained. They're used for some testing, but I just wanted to note that they fit. It's just like a regular server, they fit in the rack. All right, so I want to talk a little bit about how all these devices are connected to each other. So they're connected with a FICON cable. A FICON refers to a fiber optic connection or fiber optic cable. Okay, so this is maybe kind of a little bit boring to look at a yellow cable here, but this is really, in my opinion, the core of the mainframe. So the mainframe does not do number crunching. It's not a scientific machine used to do scientific calculations. It's used to process business transactions. So the benefit of the mainframe is, look, you're running hundreds of thousands of transactions all across the world. Think of a transaction as a credit card swipe. Every retailer who's swiping that credit card at their location, or every time you do, it's generating transactions. So there's thousands, hundreds of thousands, and millions of transactions are coming in, and the mainframes are processing them all simultaneously. So why am I bringing it up here is because these fiber optic cables are connected through a FICON card, it allows this I/O to be handled in a much more efficient way than other types of devices can. So there are literally hundreds of processors in each one of these FICON channel cards that you see these are processed in. Each one has processors to take care of the I/O. So that's just one of the reasons why mainframes can process hundreds of thousands of transactions simultaneously, is because of the quickness of these I/O cards and FICON cables. So, these are 16 gigabit and up to 16 gigabyte you can get now, and there's even faster. So the speed of these devices are getting even more and more faster all the time. I just want to give you a little scale of what it looked like. This is a FICON connection or FICON cable, and this next to it is a 2 meter, what's called a bus and tag cable. This blue cable is about 2 meters long. It weighs 2.5 kilos. It is solid copper. This is a very short one. You can imagine back in 1975 when you were hooking up all of those individual DASD units, they were all connected with this blue cable, and there was hundreds and hundreds of feet of this cable and thousands, tens of thousands of pounds of weight inside of the data centers to do that. Much more efficient with the fiber optic cable. All right, so now I'm going to jump out of the data center a little bit and talk a little bit about some of the internal features of the mainframe. But before I go, any chat, any questions coming in, Atul, anything that we should review before we move on?
No questions in the chat so far, but I would remind everybody that you are free to unmute. If you do have any questions or comments, then please do jump in and let's have a conversation. So thanks very much. And Keith, yeah, so interesting so far. I've learned a lot already.
Oh,
And it
great.
does feel like a tour of the data center. So please carry on.
Good. Thanks, Atul.
Okay.
So here's a picture of two CACs. Remember, these were the mainframes themselves. So there's two physical mainframes sitting in the data center or sitting close to each other in proximity. So what I want to do is I want to connect the two of them together so that I can increase the power and the capacity of the machine itself. I'm going to connect them together, what's called a coupling facility. So a coupling facility is another standalone processor, or it can be the internal ICF that we saw as an option as a processor drawer. So it can be external, or it can be actually running in either one of these CACs. So connecting them together with a coupling facility makes this a parallel sysplex. So it's commonly referred to as a sysplex. It doesn't have to be between two separate CACs. They can be between separate LPARs running inside of the machine or separate physical machines. So you could have two LPARs that are sysplex together, or the LPARs could be on different machines and sysplex together. So a sysplex is just a grouping of logical partitions. So I'm going to go into a little bit about what a logical partition or an LPAR, it's always referred to as an LPAR, in a minute. So the basic hardware that we looked at before is there's the CPU, the memory, and the IO that we talked about already. And on top of that is a hypervisor. This PR/SM is a hypervisor inside of the mainframe. It's commonly referred to as Prism. So this is a firmware code that runs on the mainframe that allows you to logically partition the device. So think of it as in a distributed system, VMware would be the hypervisor, or Ubuntu would be a hypervisor that you would use to have multiple guests running underneath it. That's the same thing with the mainframe. As a matter of fact, the mainframe has been doing this forever to be able to logically partition or create LPARs. So you might have heard the term, and I usually slip up and call it MVS at one point in time, so I just want to get ahead of this. MVS is just an original name for the zOS, but it stands for multiple virtual storage. So you can think of it as just an older terminology for zOS operating system. Okay, so we have multiple LPARs that are defined using this Prism layer. So it's part of the hardware, so it's nothing else that you have to run or operate. The systems programmer will control that and set that up. There's also an operating system called VM, which is a virtual machine. So you can run a ZVM system as a Prism LPAR. Don't confuse that with a VMware VM. This has been around a lot longer than that, and it is a mainframe virtual machine. And under that, you can have guests. You could have little zOSs running under there, or you could have zLinuxes, multiple zLinuxes. So you essentially have a hardware hypervisor with an LPAR that has an operating system in it. And under that, you have more operating systems. So you have a lot of flexibility on what you can do with mainframe configuration. You can have dozens of these zOS LPARs in a mainframe configuration, and they can be fully utilized and separate standalone operating systems. So when I say standalone, I mean what happens in this zOS LPAR will have no effect on what happens in this zOS LPAR. Even if they're sysplex together, even if there's a coupling facility between the two, they still are independent entities. So this gives a lot of redundancy, and that's why people will sysplex systems together. So if something happens to one LPAR, the other LPARs will take over the load for you when they're sysplex together. So there's a real good guidebook. If you haven't heard of Redbooks before, I would look them up and go through them. Redbooks really try to walk through some of the more technical and challenging things, all associated with the mainframe and other topics hardware, software, all sorts of things, but the red books are really good. And this particular red book, I have a link here, is for a Z14 system technical guide. But there are technical guides for all of the books, but they're surprisingly easy to read. So if you have an interest, I would look at those. Okay. So now inside of a zOS LPAR is something called an address space. So there are address spaces that the system uses, they're system tasks. And there are address spaces that are started and controlled by the system's programmers. Those are started tasks. And then there are TSO users. People in TSO, stands for time sharing option, but TSO is for people who are logging onto the mainframe to interact with it. So each person that logs onto the mainframe gets their own address space. So there can be hundreds or thousands of these TSO address spaces. In addition to that, I mentioned briefly, there are batch jobs. Batch jobs are workflows that are not interactive. You start it, you initiate it, and it does a series of steps or a series of jobs, and then it terminates. I'll talk a little bit more about that in a minute. So each one of these services that are run in their own address space. So the address space, I'm going to go into a little bit more detail. I don't want to lose a bunch of people, but I do feel like it's an important part of the system. So each one of these address spaces starts out identical. They're created by the operating system, and then programs are loaded into them and executed. And each one of these address spaces is a virtual copy of all the rest of them. So this is another layer of virtualization on top of it. So you have Prism with LPARs that are virtualized. And then inside of the LPARs, you have address spaces, and each one of those are virtualized. So essentially, if one of these TSO address spaces crashes because somebody wrote some code that abends and brings this address space down, because it is a virtual and a unique copy, it doesn't affect anybody else on the system. So maybe some of these system tasks failed, it would fail it because they're controlling important functions, but they technically wouldn't affect things operating in other address spaces. So you have multiple layers of redundancy and virtualness to help protect and keep that 100% uptime. So another reason why the mainframe has virtually zero downtime in most environments. Okay, so let me go into a little bit more detail on an address space just to give you a flavor of it. So an address space you can think of as a giant Excel spreadsheet. It's just a set of cells. Just think of it that way. It's 16 exabytes. 16 exabytes is 1 million terabytes. So it is an enormous amount of space. So when it is first created, say it's an empty shell of 1 million. So it's this empty Excel spreadsheet that has all blank cells. And then what happens is the operating system takes and loads some things in there for you. So it loads some certain things below the 16 meg line. Okay, the 16 meg line is important because that's what the original MVSs could only talk to. It had a 24-bit address. So with a 24-bit address, the largest number that you can get to is 16 meg. So the 24-bit address was important because that's all that they had at that time. Now, the reason I'm bringing this up is because the current address spaces are still configured the same way with this code below that line. And the reason that they do that is so that people who wrote programs that used a 24-bit addressing will still work on a modern 64-bit mainframe because of the way IBM architected the address space to allow you to do that. Now, you have to think about that for a second. That is really a genius thing. What they said is, you wrote a program, it will continue to work, and it has intellectual property that you find valuable. You don't have to rerun it. You don't have to recode it. You don't have to recompile it and assemble it to make it work in this new environment. It's just going to work because we kept the address space layout below this 16 meg line the same. So then when IBM went to the 31-bit extended architecture, that got 31-bit, you can get up to 2 gig of an address space. So when they went to that, they created an extended area, which is basically a sort of a flip mirror of this lower part. And so those programs could use that are written in 31-bit mode can use the area above it. And then finally, they went to the 64-bit operating system, and now you can get the entire 16 exabytes, which is obviously much bigger. Now, this drawing that you have is out of scale. You can see this, the top of the shared area here is 512 terabytes. So between 512 terabytes and a million terabytes, that's an enormous size on the top here. So you can't draw that in scale, but I just wanted to let you know. Okay, so when the operating system loads for you and creates an address space, it loads things from PLPA and extended PLPA and all of these other areas within the operating system. It's loading programs and modules and things into this address space for you so that everyone gets an identical copy of the address space when they start. Then what happens is you load the program that you want to execute into your area into this address space and start executing it. All of that happens for you automatically. And so, don't have to worry too much about it. I just want to say that that the address space is set up for you, and the same base set of modules or programs or load modules are included in every address space. So I know that's always a lot. When I do a live audience, interactive audience, I can look out and see the faces all staring back at me. If you've not been exposed to this, it's kind of confusing. So if anybody has any questions about that, let me know. That's one of the difficulties of not seeing a live audience. So I'm just going to go on, but feel free if you have questions, just go ahead and stop me. Okay. All right. So when I said the term you, really I mean the operating system in terms of fetching a program and loading it in for execution. So there are some programs that are in there already for you that came from the LPA. There are some that come from your own execution code. There's some JCL statements, I'm going to talk about this in a minute, called a step lib that points the system to where to load the programs from. And then there's a linked list. Now, I'm going to do an entire hour on this topic, actually tomorrow at 2 p.m. UK time. I'm going to talk about how these programs are fetched and what order and how the system does this. So just to give you an idea, every one of these topics I've talked to could be talked about for hours or days. So I'm really giving you just the tip of the iceberg on these. But this is an hour presentation I'm going to do tomorrow at 2 p.m. if you're interested. All right, so let me talk about JCL a little bit. JCL, I think, kind of has a little bit of a bad rap. It's what's used to tell an application what to do without it being interactive. So it looks kind of weird, but it's actually straightforward. So this first card is a job card. That just identifies you to the system. So when you initiate this workflow, the system knows who it is and who you are and what your level of authority is and what you're going to do. So this next card, this exec card, all that tells the system is what program that you want to execute. So I want to execute EXCEL. I want to execute this program. So that's all it's saying. And then there are cards called DD cards. I'm going to tell you a funny story. I don't want to confuse you. It's always DD, right? But when I was first learning how to be a systems programmer, I was taught by my mentor. His name was Dave Deutsch. And Dave told me that DD, this card, was your initials. So my first set of JCL that I coded, I coded all these DDs as KSs. So he loved confusing me, but in the end, he was an excellent mentor. But anyway, they are DD statements. All right, data definition cards. So these just are all cards that are needed for your program that you're executed. So these are files or data sets that are included, or workspace areas, or whatever is necessary for your program to execute. The program will expect those files to be there because it needs to use them. And then you can pass commands to the program. You know, you want to open something, you want to sort, you want to save, whatever the commands that this program is expecting, you can include those. And there can be multiple steps. So step one was this program, and step two is my program. And we're going to go into a little bit more detail on that in a second. So JCL is really very simple. It's just a way of initiating an automated workflow called batch job. All right. So the step lib is another way of showing where this program is located. So when you include a step lib card, what you're saying is the program, my program here, is located in sys3.my.loadlib. So that's what the step lib is. It's another way of identifying where I want to load my program from into my address space so that it'll execute. So there's nothing magic about any computer system. So when something happens, it doesn't happen by osmosis. There is a methodology for doing this. So when you submit JCL, how does it get into the system? Well, it gets into the system with something called JES. So you can submit it using a command if you're logged on interactively with TSO, or job schedulers like Control-M or TWS, CA7. All of those things can automatically schedule and submit things to JES, the job entry subsystem. So there's a lot of people that use JES 2. There are also some people that use JES 3. It's just a different way of initiating work into the system. They do it, you know, kind of radically different. So there's a difference between a JES 3 shop and a JES 2 shop, but the basic premise of what they're trying to do is the same. So when a job gets then submitted to JES, it's just a simple command, submit this set of JCL. JES takes it and puts it into an initiator, which is just an address space, and starts it and then knows what program to load and what files to use. So it sets all that up for it and it runs independently in a batch job. Now, one batch job will have more priority over another one, and all of that is controlled by something called a workload manager, WLM. What that does is it says all of the work that's running on the system, I'm going to prioritize which should run and what over. It's a very sophisticated piece of software because it says, this can say things like, oh, this program is waiting for this file to be free. So I'm going to not run him. Instead, I'm going to run this other one who is ready to run because it has everything that it needs. In addition to that, you can say this program is a payroll program. So it's more important than somebody creating a listing of something. So I'm going to run the payroll program over this other. So there's an entire set of there's a science and a art to setting up workload managers so that your batch work runs the way you want it to run. And then where does the output go? Well, all of the output from the job then is saved by Jez in a spool so that you can go back afterwards and look at the job. You can see this step executed, it allocated these files, and this is the output from the job. And you can see step by step everything that that workflow or that batch job did. All right, so how long can jobs run? So it's really controlled by class, by workload manager. There's a whole bunch of other things that you can do, but you can say, hey, I want this job or this started task or this batch job. I want this to run forever. I don't want it to ever stop. Or you might say, I want it to run for this many hours, and then whether it's done or not, I want it to stop. Or you can say, I want it to run until it consumes this much service units, and then I want it to stop. So there's all sorts of ways that you can control all of the workload, very sophisticated environment. So that's JES. Okay, so I'm going to talk about some of the other major subsystems that we had on the system, just to give you an idea. How am I doing on time? I got 15 minutes. Okay, so just to give you an idea, you've probably heard of CICS or KICS. So it is also an address space. It is a transaction processor. A CICS running in an address space is typically called a region, or CICS or a KICS region. KICS is very popular in Europe. CICS is more popular, I guess, in the US, but either way, it's pronounced KICS or it's spelled out CICS. But either way, it's a region. So if you think of a CICS region as kind of as a web server, it executes code on your behalf based on input that it receives. Same thing if you go to a website and you type something into a website and hit enter, the website has a server on the back end that interprets what you typed and sends output back to you for execution. That's exactly what CICS does. It can be a batch job or a started task. And when it executes a transaction, it really is executing a series of defined programs underneath. So the value of that is you can define a transaction and you can keep the transaction name the same, but change the underlying programs so that you can keep a consistent user interface to that system. It can access files, usually a particular type of file called a VSAM file. I'm going to touch very briefly on that. Or it can access databases like DB2 or IMS, and it can also use MQ series, which is a queuing system to move data from disparate systems one way or another in a cache. Okay, so you might have seen a screen that looks like this. Might have seen it at the airport. You might have seen it, at the hospital when you're checking on status of things, or you might have seen it in a retail outlet. Typically, if it looks something like this, it's probably CICS in the background. Lots of data to fill in, and you hit enter, and it processes, and it comes back with some results. Now, there are also many, many front ends that have been GUIfied that just look like any other web page that are actually executing CICS transactions in the background. So you don't have to use this green screen, but if you see this green screen, you're almost assuredly talking to a CICS system. So CICS is very important. There are 100 billion CICS transactions a day. Virtually every credit card transaction, all of the airline reservation systems, just many, many different types of use of CICS, obviously, but billions of transactions are operated every single day. Very important. All right, so let's go back to our zOS LPARs. They're connected together with a coupling facility, and you have a bunches of CICS regions running on 2 different LPARs for redundancy. All of these CICS systems are operating together. So the ones that are on the same LPAR are a system group. They're all operating together so that they can each, it doesn't matter, a transaction comes in, it can run on any one of these CICS regions on either one of these sides. This whole thing is known as a KICSplex, when you have a group of CICS regions across a 6plex. So you could have hundreds of CICS regions based on, or one, based on the demand for your particular application. All right, so let's move on. I talked about DB2. DB2 is the preeminent database system that runs on the mainframe. So DB2 is the started tasks associated with DB2 are known as subsystems. It is a relational database, and it is SQL based or SQL based. And it's the same idea is you can have multiple DB2 systems, they're data sharing, and you can connect them all together with the use of a coupling facility and come up with a wide plex of DB2 data sharing environments. Okay, so we have IMS, and IMS is another IBM database. It's made up of a database component and a DC component. So it uses a language called DLI, which is a data language interface. So IMS, though, is a hierarchical database. It has a hierarchical system for getting to particular data. So, you know, I personally think that IMS is like mostly voodoo. I don't understand how it works, but it is enormously efficient. It is very fast, and it is designed for performance in mind. The DC component is like the transaction manager associated with CICS. It's you can connect to the database directly without having CICS. But a lot of times what you'll see is an IMS DB connected to a CICS transaction. And when obviously joking when I'm calling it mostly voodoo, but it's a very complex and sophisticated system. And somehow they figured out how to make SQL work with IMS. So a relational database query engine in a hierarchical database system. So if you know a lot about it, you're pretty secure because it's a complex system to understand and learn. So IMS individually are called regions. All right, so I'm going to back down a little bit. I know I have about 8 minutes left. You've seen ISPF. It is you use it when you log on to TSO. It is a panel-driven menu system to allow you to navigate. So you see a primary option menu. You want to go to the utilities. So you select option 3, you hit enter. You go to the utilities. You want to do a data set list. So you select option 4, hit enter. You get another panel. You want to list all the data sets starting with SYS2. You hit enter, and then you get your data sets. So it's green screen. The editor is very good and very sophisticated, but it's not exactly modern looking with the panel driven interface. So there are other options. This is an example of BMC's Topaz option. You can see it's kind of the same thing. The data sets are listed over here. You can edit and browse and do all the same things you can do in ISPF. It's just a more modern interface. Here is some at the bottom. Here is some jobs that have ended and that are waiting to be viewed. So you can look at the JES pool. There are other examples of this. IBM has an interface like similar to this. There's an open source project called Zoe that has a modern interface to the mainframe. So they each have good benefits to them, and a lot of times people new to Z are more comfortable using this type of an interface than the ISPF interface. All right. So I gave the example of 3.4 when you're looking at the catalog, and I wanted to just briefly say what the catalog is. So data sets that are out there on all those hundreds of VALSEERs that you have, you don't have to remember where they all are. There's a catalog, which is exactly that. It's a lookup facility of telling you where the data sets are. So you know the data set name, you need to know what volume it's on, or the VALSEER, and you need to know what the unit type is. So if you know those 3 pieces of information, you can find a data set. You have to know those if they're uncatalogued. So the catalog itself takes those data set information and puts it into a simple lookup function, so that when you look for the data sets, you can find them. And I don't have enough time to go into all these details, but data sets can have a variety of characteristics associated with them. They're not just all sequential files. A predominant one is VSAM, which has its own access method to make it easier and quicker to get data out of the file instead of just doing a lookup of the entire data set. There's also a Unix system services facility. You know, when you log on to it, it looks just something like this, and it's exactly the same as you would normally see with a Unix environment. It's Unix branded. So log on to TSO, go right into Unix, and then you're in kind of a native Unix environment. You can list with the ls and change cd, change mod, all of the normal Unix commands that you would see. All right, I am really slow today, so I have 5 minutes left. I'm going to go to SMPE because SMPE is a mystery to a lot of people. Let me just say this. SMPE is a database of the parts that are necessary for an application. Okay, so it's a data set of parts. And it also contains a reference of how to build the application locally on your site. So when someone distributes something to you with SMPE, what they give you is all of the parts plus the instructions on how to build the part. So when you do a receive, you're receiving into the database, the CSI database, all of the parts necessary to build the application. Then what you do is you apply it. And when you apply it, it actually takes the instructions and builds the load modules, it builds the panels, rexes, messages, whatever are the parts to the program, it builds them and puts them in the files so that they can be executed. And then the last step is you accept it. And when you accept it, all that's doing is creating a baseline so that if you have updates in the future, you can apply them safely and have a baseline to back them off if you need to. So receive, apply, accept, database of parts. That's SMPE. Okay. And so you also hear some terminology around the updates, those fixes. It's called an APAR or a PTF. An APAR is used to describe the problem, and the PTF is used to provide a resolution. So when you receive a PTF, it will make changes to a load library or a panel or a message so that you receive it and then apply it, it makes those changes for you. So this is how you initially install and then how you maintain a product. You might be surprised to know that RESTful services are available as part of CICS and zOS directly natively. They're used all the time. For those of you that don't know what REST is, you probably see it all the time in a web service. Put, get, post, delete. You know, it's passing a JSON object, which is just a data element with name value pairs. But the REST web server can be a mainframe. The server client can be a mainframe. So all of this work can be done directly on mainframes. It's a modern interface to mainframe. The reason I bring this up is because this is commonly referred to as a microservice. So in the background, it might be a CICS transaction that's interfacing to a web service on the front end. So you're providing maybe a quick microservice like an account balance lookup or something like that. So these services can run and do run all the time in mainframes. Might be useful for the Internet of Things too. You can post data to the mainframe and it can adjust it. Okay, so just a quick recap, and I'm at the bottom of the hour. We talked about the CAC, we talked about Prism, we talked about the memory, FICON, OSA cards, and we talked about the different types of processors, talked about logical partitions and address spaces and JES and CICS and DB2 and all of those things associated with it, and interactive environments, workload manager. So I think we got through everything in the nick of time. Adil, what do you think?
Just coming back. So Keith, that was fabulous. And I think we learned so much. And there were comments in the chat about, wish we had this kind of presentation many years ago when we first started our journey on the mainframe. So really appreciate that. And comments are coming through straight away here. Best presentation I've seen in a while. So clear, the slides and explanation. What a great teacher. So,
Oh, wow.
Keith, well done. You've got some great feedback coming your way. We have got a few, well, we've hit the time, but we might spend a few minutes. If people do have any other comments or questions, then please do unmute yourself and ask the question now. And in the meantime, I have put the feedback link in the chat. So please do feel free to click on that and provide feedback. And I'm just going to add in also another final link really to the charity donation. So if you would like to do a donation, then please feel free to do that as well. So do we have any questions? No, I think Keith, you've covered everything in good detail, and I'm sure people will follow up with you afterwards as well. So
okay, great.
So thanks once again for that, and we look forward to seeing you again next year as well.
All right. Well, thank you, Adil. It's always a pleasure, and hopefully we'll be live next year.
Yeah, fingers crossed. Brilliant.
Yes.
Okay, well, thank you, everybody. And I think we'll close the call for there now. Thank you for your company.
Thank you. Bye now.